I have this wonderful tutorial on Introduction to Parallel Programming with OpenMP. And my goal is that you spend no more than half the time listening to me and the other half working with code. That's why having an interruption in the hardware is particularly devastating. Because I'm a great speaker, but you do not want to hear me talk to you for 8 hours on OpenMP or any other wonderful thing I could talk about. That's just dreadful. It's actually the worst way to try and transmit information to humans. You only learn by doing. So it's actually really critical that before we get going here too far, you all have access to an OpenMP compiler on a system with more than one core. We don't need lots of cores. We don't need anything fancy. I do everything on my wimpy little ancient 2015 era MacBook Air. And that's fine. All right, so let's go ahead and get started here. An introduction to parallel computing with parallel programming with OpenMP. This is awesome stuff. All right, first, who am I? I'm just a simple kayak instructor. My passion is going in the ocean and having what I call self-wetting moments. And I'll let your imagination let you figure out what that means. But big waves, whales coming up. I mean, just like, oh my God, living on the Pacific coast, it's a glorious place to be. To support myself, I take programs and I generate speed-up plots. So that's how I make my living. It's pretty cool. So I want to emphasize that the views I'm expressing here are my own. Please, I work for Intel, and we can get in so much trouble if you try and say, it's happened to me before. Well, Tim said you're building 1,000 core chips, so where is that going to be and was it going to show up? That actually literally happened. I can tell you about it during the break. It was amazing. Lawyers got involved. It was really bad. So look, I am speaking for myself, not for Intel. I am not a spokesman of the OpenMP Architecture Review Board. I'm just here to talk to you about my passion, which is parallel computing. But I've been doing these tutorials a lot of years, and I'm always very, very interested in feedback. So if there's something I do that's particularly bad, tell me about it. You know, maybe during the break, don't break up the flow, but you know, you get the idea. I want to hear about it. And if something's really, really good, I like hearing about that too, because it's a continuous feedback process. Now, the goal today is active learning. So it's interesting. I am a certified kayak instructor trainer. I train people to teach kayaking. And 15 years or so ago, I realized the way I taught people to teach kayaking was absolutely different than how people taught computing or science. And that's stupid. You know, we care about training athletes. We don't care about training scholars. So there's a very vast literature on how to train athletes. So the whole idea is, can I take the way I train athletes and apply it to parallel programming? And this is the result. It's active learning. So there'll be a lecture, there'll be an exercise. And during the exercise, I want the room to get noisy, talk to each other. Okay? There are some of you who are really experienced OpenMP programmers. Raise your hand. Come on, don't be shy. All right, yeah, a little bit. Those are my teaching assistants. All right. And there's, the old adage that the best way to learn something is to teach it is true. So if you got the exercise done and the person sitting next to you is looking really, really confused, offer to help them. The other thing is, when I give you an exercise, do it as I assign it. There's a few cases, one coming up right off the bat, where you'll see the exercise and you'll go, no, it'd be so much easier if you just did blah, 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 blah. It's like, yeah, but there's a reason I said do it this way. So always do it the way I assigned it. And then, because if you're experienced, you go really fast, play. And I mean play like, well, what does the error message look like if I break this? It does this with this many threads. What happens if I ask for 1,000 threads? How does that break? In other words, there's lots of ways to explore and dig. But always do the exercise as assigned first. All right. Now, there's at the bottom of these slides, there's a GitHub repository where all the exercises are there. The slides are there. You'll probably want that on your laptop or obviously on whatever system you're going to work on. It amazes me I have to say this, but don't cheat. Don't look at the solutions. They're there for your self-study afterwards, okay? We are not taking scores and we're not grading you. I can't believe how many times I've had people look to the solutions because they didn't want to admit they couldn't do the exercise. You know, if you can't do the exercise, that tells us something, and I want us to know it. All right, so systems to work on. We're going to come to that in a moment, but you know, there's of course the systems that aren't available. There's the NERSC. There's the systems at your home institutions. There's your laptops. I want to warn you that on there's Theta, there's Ascent, yeah. So on an Apple laptop, Apple irritates the heck out of me. It's why I am trying to transition back to Windows. I know people usually have a gasp of horror. Windows, wow. Intel won't let me have a corporate laptop with Linux. And I know that's just crazy. And Apple doesn't respect standards. And then when they stopped using an Intel processor, it's like, I work for Intel. I should use an Intel processor. So I'm going back to Windows. It's very painful. One thing that Apple does that's really, really irritating is their Xtools compiler. See why I have to say, and speaking for myself and not Intel, you know? Me publicly bashing Apple, that's probably not good. But anyway, I'm going to bash them because they deserve it. But their Xcode suite is based on Clang. There is an OpenMP Clang backend. OpenMP works great with Clang. Apple chooses not to support it because they want you to use something they have more control over. So very irritating. But on some systems, I haven't checked this on their latest Xtools, they renamed the compiler GCC. So you'll go GCC, think, oh, I got a GNU compiler. That supports OpenMP. It's like, no, it's called GCC, but it's their own Clang compiler. So if you're going to try and do this on your own Apple laptop, you need to install an actual GCC GNU compiler. So at any rate, we'll come back to that because I want us to move forward here and the plan for today. So I'm going to start with a very quick introduction to parallel programming and OpenMP. Then we're going to talk about threads because OpenMP is all about threads. And then we'll go on through. It would be really boring for me to sit here and read this to you line by line, but that's the plan for the day. So let's go ahead and get started, all right? Introduction to OpenMP. Then in a moment, we'll take a break, and everyone will get their compiler problem solved. So what is OpenMP? So OpenMP was born in 1996, and I'm really, really old. I know, I look really, really old. I was there. I was part of the group in 1996 that did the work to create OpenMP. So, gosh, I'm so old. Anyone here not born by 1996? Oh, we don't need that. Yeah. So OpenMP came out in 1997, and the goal of OpenMP was to try and make it as easy as we could make it for application programmers, you know, real scientists, not phony scientists like computer scientists, real scientists, physicists, chemists, you know, the real scientists. We want to make it easy for them to write parallel applications. And so it was a set of compiler directives, as much as could be done as with a compiler directive. So you said, compiler, on my behalf, create some threads. So make it as easy as we could. And the idea was to really simplify writing multi-threaded programming. And over the years, we've added GPU support, NUMA support. We've added a lot to it. So it's kind of depressing. You know, there's a lot of OpenMP people, actually a lot of Intel people who hate this slide and have told me to never show it. Ha! Yeah, go ahead, fire me. Here it is. The complexity in OpenMP. And I could do a version of this slide for MPI. This is not a feature of OpenMP. This is a feature of what happens to a successful programming model. Just look at C++. They have a similar problem. That is, as time goes on, someone comes and says, well, this doesn't work for this hardware. We need to add this. You know, oh, I came up with this algorithm. It's really awesome. You know, could we add this? So you get this growth and complexity. And it's kind of amazing. What I have here is a plot of the number of pages that defines the API. So I removed the introduction, I removed the examples. You know, it's just the page count to define the API. And when we started, it was around 40 pages. I would teach it, and I would cover every single nuance in one session. And now it's, 475, 500 pages. I don't think there's anybody who fluently off the top of their head can recover every single subtle little nuance. I know I can't. You know, I've read the whole new spec, 5.2. They're coming out with 5.3 and 6.0. I can't even keep up with them. But it's overwhelming. And people look at that spec and go, oh my God, no, and run away screaming, okay? But just like the MPI folks have the same problem, they don't teach the whole thing. I don't teach the whole thing either. I've defined something which I call the OpenMP Common Core. And it's 21 items from that specification. And it turns out that for most programmers, you will never use more than these 21 items. It really is that simple. And yes, there's some subtle cases where you'll need more. Okay, a lot more sometimes. But my advice is master total fluency of the Common Core. And then when you hit a wall, gosh, I really need to do this thing, and OpenMP not letting me do it, then look it up and look at the more advanced features that are there. That's how you do this rationally. And as I said, for most application programmers, they do not use more than these 21 items. So what we're going to do today is, by the end of the day, if you stick with me, you will have total mastery, total fluency of these 21 items. So that's our goal. Does that sound cool? And then you'll be able to go and, when you call your mother tonight, because all of you call and talk to your mom every night, right? Mothers deserve that love. You'll be able to say, hey, Mom, I'm a parallel programmer now. That'll be really cool. And she'll go, what? Yeah. So let's talk about the basic foundations of OpenMP. So, of course, at the bottom is parallel hardware. And this is my cartoon that covers the universe of parallel hardware. And I guess you had the parallel hardware talk yesterday, right? So you're all experts at SMP versus NUMA versus GPUs versus multi-core versus many-core versus accelerators. There's all that stuff. Yeah. Of course, I could give a day-long talk about that, but I won't. Let's just say we got our little cartoon here, which shows these clusters where the memory is fairly flat. Then they're combined together in these large ensembles, which we call non-uniform memory architectures, or NUMAs. And then you can attach to GPUs, because we all love GPUs. And unlike most people at Intel, I can say that very sincerely. I love GPUs. They're really fun. Okay? On top of that, you have the system layer. And this is, the operating system. And the operating system is going to have the plumbing for managing all those hardware resources. And OpenMP doesn't rewrite that. It uses that. So sometimes people will ask me, I have this algorithm in pthreads. That's the low-level operating system API for writing multi-threaded code. I hope all of you have more sense than to ever try and write pthreads code. But at any rate, it exists. And they'll ask, will it be faster for writing in OpenMP? It's like, no, because OpenMP is just a wrapper around pthreads. Okay? We use what the system gives us. Okay? The real OpenMP magic happens at the next level. And that is where we have, I'm sorry, I went a little too fast. But that is where we have the programming level. So there's the compiler directives. There's the runtime library and environment variables. These feed into a lower level library that OpenMP provides. So we're going to be focusing on that blue layer there today and learning what are the directives, what are some of the library routines. And then, of course, at the top are end users and the application programmers. Now, what we're going to do today for this Common Core, my slide build I forgot to kill, is we're going to keep it real simple. Because the starting point is, look, you got a bunch of cores, they share an address space, and let's just kind of assume that every single core has an equal time access to every location in memory. Okay? I hope you all know that's not true, right? Head shake, you all know that's not true? Okay, yeah. The second we put a cache on a chip, we took the symmetric multiprocessor model and just threw it right out the window. Okay? We put caches on chips in the, oh my God, 80s? And we've been talking about SMP ever since. SMP does not exist. Okay? But we're going to assume it exists. And the fact of the matter is that an operating system has learned so much over the decades how to support this illusion that it actually works pretty darn well for you to just sort of pretend it's SMP. So that's what we're going to do for the bulk of today. Later on, we can talk about NUMA and GPUs and all that cool stuff. All right, so the essence of the OpenMP syntax. I used to skip this slide because it's like, come on, you're being boring, talking too much. Okay, but I just found it's good to just get this stuff out of the way. So we have the directives, and I'm going to do this course in C because the amount of C you need to know is very, very slight. And if you're a programmer today working in scientific computing, you have to know C. Not master it. It's okay if you're, how many people are Fortran programmers? Wow, I love it. Do you know that number's going up? That's fabulous, okay? But even if you're a Fortran programmer, when you need to do low-level interfacing to the system, you're going to need C. So I hope that you're okay with C. If not, I have in that repository, I hope it's in there, is a file called learningsc.c. And it basically is this one file that has every single thing we use in this tutorial from C, an example of it, and comments that explain it. It's a compilable program. But if you're like getting lost in some of the C-isms, go to that file. But we use just the barest sliver of C. So I've had even Fortran programmers tell me they prefer having it all in C because it's really hard in a tutorial like this to bounce between languages. But look what we did in OpenMP. So in C, the compiler directives are expressed by this thing called a pragma. So I'll have pound pragma OMP, and then the name of the construct, and then a set of clauses. And then if you're in Fortran, it's the comment statement, so your comment sentinel of choice, exclamation point, $OMP, same construct name, same clauses. So by design, you learn it for one language. You can move C to C++ to Fortran with minimal extra knowledge. So even though we're doing this in C, you were learning it for Fortran at the same time. The only difference, oh, okay, and then after the directive is a block of code. And we call this a structured block. And all it means, you think about it, it's really obvious. All it means is it's a block of code. The compiler is going to lift that, pack it into a function, and then hand that function to a low-level multi-threading layer that the operating system takes care of. So it's called outlining. You've heard of inlining, where you take a function and expand it into code. This is the opposite, and so it's called outlining. So the compiler has to make some assumptions about what it can do in that outlining. And the assumption is basically you have one point of entry at the top, one point of exit at the bottom. The exception is I can put an exit or a stop statement, shut down the program. I can do that anywhere. But basically, it's a structured block, meaning a block of code where you enter at the top, exit at the bottom. That's it. Pretty easy. Now, the one difference with Fortran is C and C++ are block-structured languages. They have built into the core language curly bracket to open a block, curly bracket to close a block. It's built right into the language. Fortran is not block-structured. So we had to add in Fortran, see that example there, comment sentinel, so exclamation point, $OMP, and the construct name. Not all the clauses, just the construct name. So that's the one difference with Fortran is, we had to build into OpenMP the closed block. Other than that, yeah, everything's all set. So it's pretty cool. Now, here comes the fun part. Exercise number 1. Find a machine that you're going to use. Clone the repository for this tutorial. Verify that you can use the text editor to write a piece of code. Type in that code. Find a compiler and run this code.